I'm really totally excited to be here on this occasion. And I would like to tell you a little bit about how we will use Marvin in Earth observation and in Earth system modeling. I will bring you 3 examples that 3 members of my own group, Armin Corbin, Helena Gerdener, and Sophie Stolzenberger, that they prepared. And I would also like to mention my institute is the Institute of Geodäsie and Geoinformation, which is part of the agricultural faculty. So this is part of the scientific contribution of the agricultural faculty, how we will use the new Marvin system. I would also like to mention in this context, Earth system modeling is a relatively new scientific discipline. The Earth system is very old, as we know, but integrated Earth system modeling and Earth system research is new. But I would like to particularly mention that the agricultural faculty, together with the rectorate, has just recently decided also to install a new professorship in Earth system modeling. So we will have more people working in this direction on Marvin, of course. So I will bring you 3 examples. And the first one, what you see behind me, is the 79-degree glacier, which is one of the biggest glaciers in northeastern Greenland. And this will be about the effect of the melting of the Greenland peripheral glaciers on climate, on sea level. My second example, this is maybe closer to many of you. This is the Rhine at Düsseldorf, but as we all, well, those of you that live in Bonn, as we all know, the River Rhine also during the last couple of years, very often in summer looked very much like here in Düsseldorf. And this was, of course, an effect of the big droughts that we have seen over the last couple of years. And I will look at the monitoring droughts at the global scale. And my last example, this is actually a little bit more, it's not directly related to climate, it's about space weather effects on satellite and space infrastructure. But first of all, very briefly, how do we work in Earth system research and Earth observation? Well, a little bit maybe in contrast to what Professor Griebel says, for me, observation of the system, the lab, so to say, is close to my heart. So observing the Earth, this is what we do from the ground with observatories. But nowadays we live in a space age, so we use observatories on board of spacecraft, Earth observation satellites. And then we derive homogeneous, robust, consistent observational records from these raw observations. And that's already something where we use supercomputers quite often. And that helps us to describe the change in the environment. Then, and here the understanding starts, we confront these observational records actually with numerical simulations. And these are produced by what we call Earth system models. And that's, of course, where we really need high-performance computing and production runs. And then we are able to either confirm or reject our scientific hypothesis. We know something. We may know why we have more droughts, or maybe we don't know. This is what actually leads to an improved understanding of the causal relationships. And then finally, we start to integrate our observational records with the numerical models in order, you would say, to bring these numerical simulations closer to the reality, which is what we observe, to fill the gaps and to improve the resolution. And of course, that's again high-performance computing. Now, coming to my first example, we know that 25% of the current rise in global sea level is actually caused by the melting of the peripheral glaciers in Greenland. And that's not, the world's ocean do not rise like a bathtub, it's not uniform. You will see this on my next slide. But the biggest question is probably the water that melts from the ice sheets, that's fresh water, and you all know the oceans are salty. When you add fresh water into a salty pool of water, we will disturb the density field that will create density gradients, and that can actually create currents in the ocean. And that means that this inflow of fresh water can disturb the big current systems that we have in the ocean. For instance, the Gulf Stream that brings warm water to Europe and that maintains the climate that we have right now. There was a movie a couple of years ago. The movie was called The Day After, and that was a very drastic, let's say, showcase of how the future could unfold. And my question will be now, are we already on the way to that? So this is what many of you may know from the IPCC reports. It's observed sea level rise. This is actually from the last 70 years or so. And then we have the different projections. But on which path are we? This is what we observe from space with satellites. The map shows you a global distribution of trends of sea level rise, is where it's red, and trends of sea level fall. There are actually places in the ocean where the sea level falls. So it's very much dependent on where you live. And will that be maintained, these patterns, for the next 50 years? We don't know this. These are the observing systems that I mentioned. We have fleets of satellites that observe the ocean surface with radar pulses. Now, what we did is what's called a housing experiment, where we simulated the freshwater inflow from the Greenland ice sheet over like 50 years into the northern Atlantic. And our causal hypothesis is, is that now visible is this effect visible in our observations of the North Atlantic, observations of sea level change, of temperature change, of density change. Now, for the mathematicians and physics people here, we have to solve the Navier-Stokes equation, we have to solve state equations, we use finite element or finite volume method. We use actually a model that was produced at the Alfred Wegener Institute, and this is the institution where Dr. Barbie comes from, so for him it's maybe a look into the past. We also collaborate with the Alfred Wegener Institute for Polar and Marine Research. And it's a computation that I have to admit we had to do in Jülich because Marvin wasn't there at the time. And the figure on the right-hand side, now shows you where the simulations fit well, and this is where it's red, or where they don't fit well with our observations. So you can see for large parts of the North Atlantic, there are patches where the simulations fits well, but many patches where they don't, so it's a mixed picture. It's difficult to make a good, to say we can prove our hypothesis here. But there are also two big red patches. One is in the Baffin Bay, and the other one is to the southern tip of Greenland, where we really can say our hypothesis, there's more freshwater inflow, and we see this already in our observation, that seems to be true. And it also means that simulations can tell us these are the places where we need to go, where we need to look at, where we need to build observatories. But it's also one of the outcomes here, higher resolution is still required. I want to show you a second example, which is the example of drought. Droughts at the global scale are the natural hazard that surpasses all the other natural disasters in terms of economic losses. And the droughts are expected to increase with warming temperatures, with climate change. I should also remind you that agricultural drought, economic drought, differs from the absence of rainfall. The tools that we typically use to understand droughts are hydrological models, but hydrological models are made by humans, they're coded by humans. They represent the knowledge that many experts can put into these models, but there are many physical and anthropogenic processes that are missed in these models. And also you should remember, water management is a political issue. Many countries that don't provide actual data how water is used. So we have satellites that can observe the absence of water on the ground. It's the gray satellites, but this is only with a resolution of 300 or 400 kilometers. which is totally insufficient for what we want to achieve. The lower figure shows you a map of how the continents are drying and how they get wetter as seen from the satellites. So where it's blue, we have more water over the last 20 years, for instance, in the central Amazon, but you see also large parts that are red. This is actually where we have less water stored in the groundwater, in the soil, where simply water, where we are simply losing water. The top figure is what the model produces. A hydrological model produces much more details, but it also misses the big trends. This is because of the deficiency in the models. So what we do now is what's called data assimilation. We try to nudge the models in a way that they represent what we observe with our instruments, satellites, observatories. And this is a technique where you have to run many model simulations in parallel, so coming back to the parallelization aspect. So it's extremely important. We can do this research only since we can parallelize our computations. This was done on the Bonner system. On the left-hand side, it's the presence of water or the absence of water as seen by a model. On the right-hand side, seen by a satellite at 500 kilometer altitude. And in the middle, this is when we integrate everything. And there are very few groups that are actually able to do this. And I'm proud to say that we meet up in January with the NASA Goddard Space Flight Center group. They believe they are at the forefront of this. In the meantime, we believe we can surpass what they do. And we also produce, of course, droughts map of this new information. On the right-hand side, this is what the satellites are able to produce. On the left-hand side, much more detail when you integrate this with the hydrological models. So the implications, I think, are manifold. This is also that we apply with coupled modeling in the SFB that Petra mentioned, but this is also a topic where we provide recommendations for future satellite missions to the European Space Agency. My last example, and it brings us back to the high altitude atmosphere, and the figure that you see on the top right, this is a funny figure. You may remember in 2018 there was a Chinese space station, it's called Tiangong, and in 2018 the Chinese lost control of the space station. I mean, it's basically like a couple of buses, and there was no control anymore, no data transmission, and the space station was bound to fall to the ground. And what you see is a prediction of the re-entry created by the European Space Agency, and basically this prediction says that everywhere between plus minus 60 degree latitude the space station could fall to the ground, which is saying it's totally impossible to predict the ground, let's say the place where such a piece of space debris would hit the ground. Well, this can be improved a little bit with very little lead time. Why is that so difficult? The reason for that is that a satellite, a space station, a piece of space debris, also a meteor, passes through the atmosphere, and at the altitude of a space station, we have an atmospheric density of a few hundred molecules per cubic meter, which is nearly vacuum, but it's not vacuum, and these few molecules, they break the satellite, they decelerate the satellite. This is the effect that you see when you're bicycling. You always think that you have the wind against you. This is basically the drag force of the atmosphere, and it's also what happens in space. Now, is that predictable? The problem is that the atmospheric density outside of the Earth is very much forced by the sun and by the magnetic field. So it's the solar, electro, and ultraviolet input, so to say. And this is very difficult to predict. So we use numerical models that represent all these processes, the magnetic shield of the Earth, the solar wind, also the tides, to actually represent how the atmospheric density around the Earth expands or how it shrinks with the geomagnetic field and with the solar wind, we use the general circulation models. And of course, we want to be close to reality, so we assimilate observations from a few satellites into these models, and we're able also to improve the predictions. And I'm almost ready with this presentation. This simulation, provided by my PhD student Armin Corwin, shows the neutral mass of the density evolving in time. On the right-hand side, you see the electron content of the high altitude. And you see that on the left-hand side, the neutral mass, so our atmospheric envelope, really reacts in sync with the electron content of the high altitude. So it's like the breathing of the Earth's air envelope. And it's only possible with a supercomputer. So to wrap up, we are ready for Marvin. Thank you very much.